Welcome to today's custom-tailored deep dive. You look at an industrial dashboard. You see a dial with the needle resting securely in the green, and you just assume everything is fine, right?
Yeah, you assume it's all under control.
Exactly. There's this comforting expectation of precision. But when you step into the violent, high-pressure world of heavy mineral processing, those comforting dials are essentially lying to you.
They absolutely are.
Today, we are looking at an operational landscape that is completely blind to its own most dangerous bottlenecks. We're journeying into the dense mining corridors of places like Odisha to uncover a massive, invisible structural failure.
And, we're exploring how shifting from blind mechanical force to real-time acoustic data is about far more than just saving money.
Right, it is fundamentally about changing human safety. And we've got a great stack of sources for you today. We're pulling from an academic paper in industrial and engineering chemistry research on hydrocyclone optimization, a University of Cape Town thesis on slurry rheology, some product specs for rheonics inline meters, and field notes on restorative engineering.
It's a lot of ground to cover.
It is. So, okay, let's unpack this. Before we get into the tech, we have to understand the physical reality of this problem.
Yeah, we have to picture the intense environment inside these mining corridors. In mineral processing, the whole operation relies on these massive devices called hydrocyclones.
Which are basically giant steel funnels, right?
Exactly. Giant, multi-story steel funnels. Process engineers pump millions of gallons of mine material mixed with water, which they call a slurry, into these funnels at high velocity.
Right, and the centrifugal force spins the heavy, valuable minerals at the bottom and sends the lighter waste out the top, like a giant industrial centrifuge.
That's the idea. But the complication comes from the financial pressure. Pumping water is really expensive.
And every drop of water taking up space in that pipe is space that could be valuable ore.
Right. So to maximize their yield, process engineers intentionally push these highly abrasive mining slurries past a 50% solids concentration.
These are thick mixtures, right? Full of silicates, iron, chromite.
Yeah, very dense materials from UG2 ores. They're trying to move as much rock with as little water as possible. But that introduces a severe physical consequence.
Okay, what happens?
Well, according to the data in the Cape Town thesis, right around that 50 to 60% solids threshold, the slurry hits this inflection point.
An inflection point, meaning it stops acting like a normal fluid.
Yes, exactly. The friction between the particles skyrockets. It becomes what we call a non-Newtonian fluid. The viscosity just spikes exponentially.
Wow. So trying to push that is like aggressively sucking a thick, chunky milkshake through a paper straw. Eventually, the physics just break down.
Actually, it's even worse than a milkshake. It's
Yeah.
more like a giant pool of cornstarch and water. If you stomp on it, the particles lock together and it instantly acts like a solid wall.
Oh, right, oobleck. So inside those pipelines, the massive feed pumps are essentially stomping on the fluid.
Exactly. The harder the pump pushes, the more violently the slurry resists. And that massive spike in viscosity actively retards the rotational motion inside the cyclone. The centrifugal separation just dies.
Wait, if plant managers know that 50% is the danger zone where the physics break down, why do they keep pushing it that far? Why not just add a little more water?
Well, there is this eternal tension between operational stability and the relentless pressure to hit yield targets. Adding water thins out the slurry, sure, but it decreases throughput.
So they are financially incentivized to walk right up to the very edge of the cliff.
Right, to squeeze every ounce of efficiency out of the plant.
But they are walking up to the edge of the cliff with their eyes closed. Reading through these sources, the way they monitor this chaos is completely inadequate. They essentially aren't monitoring it at all.
Yeah, they rely on mechanical feed pump pressure to monitor the flow. And in this kind of environment, that is a fatal miscalculation.
Because pressure is a lagging indicator.
Exactly. By the time the viscosity has spiked and the heavy rock has started settling in the pipeline, the mechanical pressure gauge hasn't registered a drop yet.
The needle on the dashboard is still in the green.
Right. And by the time that mechanical gauge finally twitches, the dense slurry has already settled. It's too late.
And the consequence of that is just brutal. The cyclone bypasses and the bottom exit, the spigot, just catastrophically blocks.
Yeah, the industry calls it roping. The discharge turns into a thick sludge until it completely chokes and production violently halts.
What's wild to me is that you'd think everyone would want to fix this.
Well, what's fascinating here is who actually profits from this blindness. You'd assume the industry wants to solve it, but certain incumbents make a lot of money off the failure.
Like the pump vendors.
Yes, the mechanical pump vendors. When you run blind and experience heavy settling, it wildly accelerates the wear on the pumps. The impellers get chewed to pieces by the dense rock.
So the vendors benefit from predictable, accelerated replacement cycles. That is a terrible incentive structure.
It really is. And the chemical suppliers make a fortune off it, too.
Oh, right, because of the downstream process.
Yeah. When the cyclone operates blind, it loses its classification sharpness. It does a terrible job separating the valuable rock from the dirt.
So the plant has to dump all these extra flotation regions downstream just to compensate and recover the minerals.
Exactly. So the incumbents selling chemicals and replacement parts have zero motivation to help the plant measure real-time physics.
They're just selling Band-Aids. But we really need to talk about the darkest part of this failure, because it's not just about money.
No, the human cost is the real issue.
When a high-pressure pipe blocks with abrasive rock, human operators are forced to step in. They have to manually clear these heavy, hazardous pipelines. It's essentially a pressurized rock bomb.
Right. It places humans directly in the line of fire. So the obvious answer is better data. They need to catch the spike before the pipe chokes.
But how do you get sensitive data out of a pipe filled with supersonic abrasive rocks? If you stick a normal sensor in there, it's obliterated in hours.
Which brings us to the first principles for founders in heavy industry mentioned in the sources.
Sure.
The core rule is that the physical environment dictates the data strategy.
Yes. You can have the best digital control loop, but if the sensor feeding it dies in a week, you just have a liability.
Exactly. Historically, they tried using nuclear gamma densitometers to avoid the wear.
Which introduces massive radiation hazards and regulatory nightmares. Not a great solution.
No. So the transition had to move away from hazardous nuclear sensors and fragile invasive probes. They needed acoustic measurement.
And the sources highlight the Rheonics IFC15T34N SRD as the blueprint for this.
Yes. The specs on that sensor are incredible. It's built from 316L material.
That's a highly corrosion-resistant stainless steel, right?
Right, and it can withstand 200 bar pressure. That's roughly 2,900 psi.
Wow. But the form factor is the really brilliant part. Most importantly, it connects via a standard 1.5-inch tri-clamp or 3/4-inch NPT, and it sits flush against the flow.
That flush mounting is everything.
Because it doesn't protrude, the abrasive silicates can't shear it off. It survives the violence by just refusing to stand in the way.
Right. It utilizes the boundary layer of the fluid to protect itself.
Right.
While sending out these microscopic, high-frequency acoustic vibrations.
And it measures how much electrical power is needed to keep vibrating, which translates directly to a real-time viscosity measurement.
Exactly. So now you have a sensor that actually survives.
Which brings us to what happens when you actually turn it on. There was a 30-day field test in the sources that was just mind-blowing.
Yeah, that test is a perfect example. They swapped out their lagging mechanical pressure gauges for these real-time acoustic sensors.
And because the acoustic sensor measures actual rheology, it caught the exact moment of the viscosity spike.
Seconds before the mechanical pressure dropped.
That is the crucial part. It caught it seconds early.
And if we connect this to the bigger picture, reducing that data latency provides an asymmetric edge. That tiny window of time allows for closed-loop automated feed pump adjustments.
So the sensor detects the thickening, sends a signal, and the pump automatically dials back. The spigot never blocks.
The plant takes total control of the classification sharpness curve. They stop destroying impellers, and they stop overpaying for chemicals.
It's incredible, but the emotional core of this whole thing, for me at least, is the concept of restorative engineering.
Yes, the anecdote about the 6-axis cobot.
Right. An engineer deployed this robot in an explosives factory. The corporate guys measured success by ROI, but the engineer measured success by the text messages the worker sent home saying, "I'm safe tonight."
That is such a powerful metric.
It really is. Technology shouldn't just replace people for the sake of cutting overhead. It should restore their safety and dignity.
And by automating the pump adjustment with real-time rheology, human workers are permanently removed from the line of fire of those catastrophic pipe cleanouts.
Exactly. You are building systems to absorb the violence of the physical world so human beings don't have to. So what does this all mean for you, the listener?
It's a question of what kind of data you rely on in your own systems.
Right. Are you measuring the consequence of a failure after it happens, or are you measuring the catalyst that precedes it? Because managing by consequence is a very easy trap to fall into. Lagging indicators are loud and easy to see.
But true control only happens when you catch the subtle shifts before the system breaks.
So, to summarize our journey today, We went from blind, lagging mechanical pressure in these violent mining slurries to flush-mounted, real-time acoustic sensors.
The sensors that provide an asymmetric edge and actually protect human lives.
Exactly. And I want to leave you with a final thought to ponder from the expert side of the table here.
Yeah, think about this. If the first principle of heavy industry is that the physical environment dictates the data strategy, consider the broader AI and predictive models we rely on today.
Ah, that's a great point.
How many of our most advanced digital algorithms are currently failing? Not because the math is wrong, but simply because they're being fed by lagging mechanical pressure indicators rather than real-time catalysts.
A brilliant algorithm fed by lagging history is still only predicting the past. Thank you so much for joining us on this deep dive. We hope it inspired you to look closer at your own dashboards and find the true control points in your own systems.
Keep looking for the catalyst.